The 741 OpAmp is a integrated circuit with complex layers of NPN transistors with some PNP transistors and diodes, all mounted on a single IC housing. Although many different types of housings or models of the 741 are available, the dual inline is the most popular and most often used in everyday electronics, specifically by hobbyists. It is very close to ideal, and as a result, that's the one that we most typically use. When looking at the 741 OpAmp, it comes in an 8-pin housing. The half moon cutout indicates that this is pin number 1, 2, 3, 4, and then 5, 6, 7, 8. As this is an integrated circuit, firstly we must connect it to a power source in order for it to be able to operate. So pin number 7 over there, that is my positive VCC pin. That's where I'm going to connect the positive supply voltage. Pin number 4 over there, that is my negative VCC or negative VEE pin. That is where I'm going to connect my negative supply. Now the OpAmp typically runs on a dual power supply, so that it's got a positive voltage, a negative voltage, as well as a 0-volt reference voltage connected to it. Pin number 2 over here, this is my inverting input. Now the inverting input function is that it takes the voltage that we apply to pin 2 and it gives us the inverse of it. In other words, it takes the voltage and multiplies it with -1. So if I apply 1 volt to pin 2, the OpAmp actually reads it as -1 volt. Conversely, if I supply minus or negative voltage, let's say -2 volts on pin 2, it reads that value as +2. Pin number 3 is my non-inverting input. Works exactly the same as my inverting input, however it takes that value that you apply to pin 3 and it keeps it as it is. Pin number 6 is my output voltage. So the OpAmp will switch or amplify in accordance to the circuit it's connected to, and I will read my output voltage on pin number 6. Pin 8 is not connected, and that leaves pin 1 and pin 5. Now pin 1 and pin 5 serve as my null offset pins. Now the null offset pins are literally used to calibrate the accuracy of the OpAmp in more complex circuits. Basically how we apply the null offset, the easiest way is you connect a potentiometer or a variable resistor that has a value of 10 kilo ohms between pin 1 and pin 5. In the variable leg you will connect to your 0-volt point, and then by adjusting the value of the potentiometer you can then adjust the null offset or the accuracy of the OpAmp. The symbol of the OpAmp is indicated as a triangle. The line that comes out of the corner, that is my V out, in other words that is pin number 6. Then I've got my non-inverting as well as my inverting inputs, so that'll be pin number 3 and pin number 2, and then we've got our positive V and our negative V, positive and negative supply voltages, that connects over there. Sometimes, or very rarely at school level, we use the null offset. So as a result, we do not indicate the null offset pins 7 and 1, no 7 and 4, sorry. If, however, we do choose to use the null offset pins, we will indicate those on the side over there like I did with the red. However, if we're not using them, then we will not draw those pins on the OpAmp. So going back to the basic, or to the component, we see that there is my two inputs that lead to my output over there. That is my inverting, so that shows the minus there. That shows the plus because it's the non-inverting. That minus and plus, by the way, is interchangeable depending on your circuit diagram for neatness of that circuit diagram. And then you've got the negative supply that goes to pin 4 and the positive supply that goes to pin number 7. So when we've got our OpAmp and it is connected into a circuit, we've got the positive supply, the negative supply, V out over there, and we've got our non-inverting and our inverting inputs on the left over there. The way the circuit is configured at the moment is in an open loop condition. In other words, there is no feedback from the output to the input. So what we've got there is my open loop, whereby the feedback value is infinite. When we've got an OpAmp in this condition, it serves as a switch. In other words, my output voltage will either be equal to the plus V value or the minus V value, depending on which one is bigger. When we've got a situation plus V minus V, V out, where my output connects back in some way through a component to one of the inputs, that is called a closed loop. So thinking back of the transistors, when we've got a scenario like this, the output is equal to positive or negative supply value. When we've got a feedback condition, we've technically placed the OpAmp into the active region, whereby it serves as an actual amplifier, whereby it follows the input waveforms and then adjusts the output waveform in that condition. This is a closed loop, closed loop. When we've got the situation where the inverting is greater and the non-inverting is smaller with reference to each other, then my output value will be negative saturations level, or negative saturations value. If I change so that my non-inverting is greater than the inverting input, then it switches into the positive saturation value. In a closed loop system, we can have 4 conditions. Let's put all the non-invertings on top and all the invertings on the bottom. So if I apply 0 volts on my inverting and I apply a sine wave on the non-inverting, these are all closed. I supply a sine wave on the input and 0 volts on the inverting input, then my resultant will be the value of the, or in the same fashion as the input. So I put a sine wave in and I get a sine wave out. If I am to swap my inputs, in other words 0 volts on my non-inverting and a sine wave on the inverting, the result will be the inverse of my sine wave. So it causes a 180 degree phase shift. If I am to supply inverting with a sine wave and non-inverting with a sine wave, because these inputs are differential in nature, they literally take the one value and subtract the second value. So I can see that that signal and that signal is identical. So if that is positive 1, my inverting reads that positive 1 as a negative 1, and when it adds it together, it's going to give me 0 volts. So as a result, if I've got the exact same value applied to both, I should get 0 volts. Now op-amps tend in practice not to do that, and that is what the null offset pins are used for. If I take my inverting and I apply a sine wave, and my non-inverting and I apply an inverse sine wave, my resultant is that these two waveforms are subtracted from each other. That causes a sine wave on the output that is double the size of the input voltages. Now the typical operating voltage for the op-amp is, or for the 741 op-amp, is positive negative 44 volts. The differential input voltage, in other words the voltages that I can apply on the input, cannot exceed a potential difference of positive or negative 30 volts. And for additional voltage, feel free to do a search on the 741 op-amp, specifically with connection to the data sheet. Now for the ideal op-amp, and with all the explanations, the op-amp, the circuits are going to be explained in accordance to ideal conditions, or the ideal op-amp. So the ideal op-amp has the following characteristics. Input impedance is infinite in size, in other words it cannot conduct any current on the input side. The output impedance is 0, in other words there is no limit to the output current. The open loop voltage gain is also infinite. In other words, it switches to the value of the supply voltages, positive and negative, and it has an infinite bandwidth. In other words, irrespective of the frequency, it will react exactly the same. The common mode rejection ratio is 0 decibel in the ideal op-amp. Now the common mode refers to this scenario we have over here, where both inputs, if the same voltage is applied to both inputs, the output switches to 0. In practice, if you supply this scenario, then the op-amp will automatically select one of these two as its operating range. But by applying the null offset pins, I can now set that common mode rejection ratio so that if I do get both inputs exactly the same, that my output will switch to a value of 0. Additionally, the ideal op-amp is unconditionally stable and it has differential inputs. .741 OpAmp is primarily used as a switch or as an amplifier.